Dear friends, I'm going to explain here my own works based on what is electron spin, why electron spin is 1 by 2, and what is the relativistic origin, means what is the Dirac 4-component amplitude in the matter wave function. I had already made 2 videos over this, that what is electron spin, why does electron has a spin 1 by 2, and uploaded on my channel. See my channel. The name of my channel is Physics and Universe, and there are 2 previous videos. What is electron spin? 0. What is electron spin and why electron has a spin 1 by 2? I had already made my videos over this. And there I explained that the electron has a longer wave-like structure, that is longitudinal type of wave, and there's a transverse-like wave is over it in transverse motion, and that makes 1 by 2. I had explained everything there. These are my works. These are not proven research theory. These are my works. Now see, today I'm going to explain that this is the Dirac matter wave for electron, and Dirac has taken 4 components of amplitude instead of Schrödinger has taken 1 component of amplitude while expressing an electron with a matter wave. But Dirac used 4 components of amplitude. Why? From where the idea came? Dirac used relativistic concept, relativistic energy to drive the equation for electron, and he got these 4 components. But what is the physical significance? How we think about, how we physically imagine what type of situation is it that explains these 4 components. Let's see here. As we know, as my heading is, can matter wave geometry explain electron spin? A qualitative hypothesis. These are my works. These are not proven theory. I'm working on it. See. This is a matter wave, a complex matter wave, which is used to represent a free electron. This is for a free electron, and as we know, free electron, the complex matter wave, has no definite shape inside. It looks like that the free electron in a wave format has spread throughout the world, throughout the infinite region, infinite vast space. But to become a good quantum analysis, or whenever we talk about certainty about the quantum analysis, we have to think about something which has logic. If we tell that it's infinite extent, that is, it has a lot of uncertainty. I'm going to tell you that for a free particle, the wave, okay, in the standard theory that the wave spreads out up to infinity. But here I'm thinking about it is also some definite area, definite domain where the wave is oscillating. See here. It's very long, very, very long. That's why I call it free particle. See, it's moving by velocity v. And all the points in this wave is moving with the same velocity, and the frequency and wavelength of this wave is identical for everybody here. Now here is a twist. Suppose some parts of the wave has gained some high velocity, okay, gained some high velocity, and that part of the wave which has gained the high velocity will move now with high velocity, and the other part where that velocity hasn't touched yet feels with this velocity still, and there will be a difference in the velocity. Think about that, and this goes to each and every point, and that will bring some different analysis, that will bring some surprising analysis during that matter. Let's see here. This phenomena, this changing velocity goes to each and every point. It passes through each and every point, every part of this wave, but for ease I'm explaining over two definite sections. See here. Look at this wave. This, and there's the other section here. See, now there are two definite sections of the same matter wave. Earlier, this matter wave for a free electron, representing a free electron, was moving with velocity v. All the parts, all the points over the wave was moving with the velocity v. Now, as I told you, my analysis starts from a single point of the wave and it passes through all the other points in the wave. But to ease, I'm showing over two definite sections. Think about two definite sections. This section of the wave suddenly gains very high speed. Very high speed v. Forget this. It's a very high speed v. Sorry, I'm writing u. Earlier speed was v. This was previous speed now. Now what do you see? This section is still moving with the velocity, previous velocity v. But this section has gained a very high speed u v. And think about, within a wave, within the same matter wave, it looks like that there are two observers. One observer is this, other is this, and this section is moving with high speed. Different than this means this section of the wave behaves as an observer for this. According to standard theory of quantum mechanics, which is explaining electron and its spin, the same portion of one single matter wave are not two observers. We can't take them. But here I'm thinking about that, yes, we can take it. I will prove this quantitatively in my other videos. In this video, I'm just analyzing it qualitatively. See here. I think about that, if it expands up to a vast majority of space, infinite extent, then it has many observers there. Each and every point of the wave behaves as an observer. See, this section, name this section as AB, and this section as CD. So what is the conclusion of this figure? That CD is a high speed moving wave while AB is a normal moving wave. Means for ease, we can think that this is in rest. We can also think that this is in rest. And in that case, it will be like that Doppler shift. Relativistic Doppler shift. What happens in a relativistic Doppler shift? If a wave is approaching towards a stationary observer, then he notices increased frequency and decreased wavelength. Similarly, if the wave is going away from the stationary observer, then it notices increased wavelength and decreased frequency. It also occurs in the case when the observer is not stationary, but it is moving at a different speed than the wave. That's the same thing as here. This portion and this portion. And this is the point of contact. Assume it, the point of contact. So higher speed generated here reaches to this point, and then this wave will go with that higher speed. It takes some time. Let this time will be del t in its frame and del t dash in its frame. Means the higher speed generated here reaches to this point, and then it starts pulling AV section this way with the same speed, and this will take some time. According to AB, in the reference frame of AB, AB notices that the highest speed generated in CD starts pulling me with the same speed in del t time, while this wave notices that no, in del t dash time I started pulling away with the speed I generated. See, del t time in AB reference time in which AB got pulled with speed, high speed u, high speed u with respect to AB. And the same thing here, del t dash is time, let me write this as this, del t dash is time in which AB got pulled with high speed u with respect to CD. For this same event, this section notices this time, this section notices this time, and this gives us time dilation. Means time dilation is telling us that for the same event, here del t dash and here del t, means there is some disagreement of the time. And if these both sections have any other mode of information, means through which the information can pass like light, then they will exchange their communication that you have taken del t dash, I have taken del t for the same approaching speed u, and that gives us a time dilation. Means either of them has shortage of some time for the same event, and that will be, in the shortage of time means there must be some changing or there must be some disturbance in the space around them. What space will be that around this matter wave? According to standard theory, the space around matter wave, we call it electron field or quantum electron field. For photon, it is like electromagnetic field. Okay, so here we notice is that the time dilation, the disagreement of time between two different sections of the same matter wave generates some disturbance, some twisting, some tearing in the quantum electron field around it. And the disturbance in field gives us some wave, and that's why there are the presence of some other type of waves here despite this matter wave. Let's see here how it happens. As we know, if it's moving towards this with higher velocity, it brings some extension in the wave, and this section is behaving as an observer for this wave, this section of wave. It notices that this section of wave is pulling me with higher speed, means that it is approaching away from me, approaching just like a photon Doppler shift, approaching away from me. And in that case, it notices a decreased frequency and an increased wavelength. Understood? And as it's increased wavelength, so if it's increasing in one dimension, it shrinks in other dimension. And there were y and z axes. There you get shrinking, means the disturbance in the surrounding field, electron field, and that gives us that tangential waves are approaching towards it, and those waves have their wavelength. So one increasing wavelength along this direction and several shrinking wavelengths in this direction which are approaching towards it. Notice this, from the motion of 1D, there are effects in 3D. And that's concluded here, because Dirac mentioned that these amplitudes, these components of amplitude are orthogonal. They are not in same direction. They are, suppose one is in x direction, then other in y and z direction. According to Dirac, two of them are 0. So two of them are 0. 0. Two of them are 0. If this is 0, maybe this might be 0. So out of the 4, only two have values. One has major value, another has minor value, and the rest 2 are 0. And they switch their position to get positron. See here, that's a different case. I'm just explaining why it feels that there are 4 components of amplitude, and all those are orthogonal. One is along the motion, main motion, and other 2 or 3 are in orthogonal motion. Let's see here. Let's see what I explained with a simple demonstration. This is the main longitudinal component of matter wave explained by me. Now see here, if one portion is increasing, what are you noticing? We are noticing here that it is increasing in this direction. That will give a shrink to all this. This is like a tensor. Think like a tensor. It shrinks in this way. And there will be, if increasing wavelength is in this direction, then the waves rushing towards it has reducing the wavelength here. That's tensor. Now see on the equation on the board. Go to the board. Yes, see here. As I showed by a demonstration where the wave shrink, means the field around the electron wave shrink, means there's a rushing wave towards it. If it expands, then rushing wave towards it. And in this way, we have a tensor of wavelengths and frequency. Let's see. This is along this axis. Then this shrink to all the rest dimension. And along expands along this, gives amplitude in other dimension. That's according to Dirac. Means in the Dirac equation, we can think why these all these 3 are orthogonal to each other. See, the tensor of wavelength. See, the tensor of wavelength, lambda xx, lambda xy, lambda xz, lambda yx, lambda yy, lambda yz, lambda zx, lambda zy, lambda zz. This is a wavelength. When it pushes it at this point, it feels that yes, there are wavelengths. This is along this, and this is, and all other are perpendicular to this, except this xy, xz, yx, xz. Why this? These are not perpendicular to this. Tilt it down once. See here. If it's expanding in this direction, have you paused it? Okay, no matter. See, if it's expanding along this, so wavelength along this is xx, and it shrinks. So this is yy wavelength, and this is zz. This is yz. This is yz. Now see, for zx and for xy, see, there must be some component in this direction. That is xy, and there must be some waves rushing, some disturbance in electron field or waves rushing towards it is in xz, and that could also be there. But for ease, to understand easily my work, I removed these components. Okay, now show the board. Here, for the ease, I have ignored these things. So you can take 0. You can take 0 here. Take this 0. Ignore this. Then all these 4 are orthogonal to this. Okay, and relative to this segment feels measures the relative values of this as this. Okay, this is dash. This is the relative of this. What it measures? This. This is the tensor, relativistic tensor of the wavelengths. Again, here I can tell you, or I don't know, that these are 0 or not. These are 0 with respect to this. There may be some value, but as I had ignored it due to the 4-vector Lorentz transformation of wavelengths and frequency of matter wave, we can do this. I will do this in the next video with my more research works. For ease, I can give you some hint that as Doppler shift in longitudinal way and in transverse Doppler shift, relativistic Doppler shift helps you to understand this concept. But we can't apply Doppler shift. We have to apply Lorentz 4-vector transformation. So I have explained my work. This is just hypothesis, not proven work. I'm trying over this. It has some dissimilarity with the standard theory of electron, Spinor electron. But here, these are my works. I invite everybody to suggest me my errors or to criticize me. And thanks for the watching.